So before I really start with this, I want you to check this out. You can see this illusion, right? So look at the blue lines, blue strips. Are they parallel? What do you think? Hello, are you guys there?
They are parallel, but they do not look so.
Okay, yeah, exactly. So this is something which we'll be looking into and studying a little more in depth. So to start with, I'll just blur this image out. Okay, now they look pretty parallel, right? It is very evident that they're parallel. So what do we see here? Just by adding some decorations on top of this image, we were able to trick our brains into believing it's something else. At least it appears something else. So it's the exact same strips, blue and black. Just by adding few decorations on top, an illusion has been created. So the we've seen human beings can be tricked, and there's so many such illusions out there. So if humans can be tricked, the question now here is, can we trick machines too in a similar fashion? Okay, so that brings me to the topic of adversarial machine learning. So the first question, we'll be looking into these four questions in specific. So the first one was a question about tricking and fooling machines, which is the base for our context today. Then we look at its implications. What if we can trick? What are its implications? Then we look into few existing attacks, few simple approaches, actually very simple, and I'll briefly go through a few defense mechanisms on how to prevent such attacks. Okay, so there's this concept of adversarial images which I'm going to be dealing with for the rest of my talk. So these are images specifically created by an attacker to fool a system. So in the first case of the optic illusion, we saw the decorations on top. They've been devised carefully, and it wasn't just arbitrary. They have been devised with some criteria so that your brain is tricked. Here, adversarial images are something very similar. They appear to be normal images, but something is done to it so that it is able to trick the existing systems. So let me give you an example of adversarial image. On the left-hand side, you see a picture of a dog. It's fairly evident, and on the bottom, the caption, it is the output of a classifier, a simple classifier. So the first picture, the classifier says it's a dog. Now let me add some noise. Okay, some noise. We'll look into the noise aspect later on what this noise is and how it's generated. But for now, let's say we're adding this noise to the initial image, and now the image, this is the resulting image. And to human eyes, it's fairly the same, unless few blurred spots here and there, but it's still the same for us. But now you pass this image to the classifier, it says it's an ostrich. Okay, so just by adding this noise, and it's been carefully devised, it's not arbitrary, you can fool the system into saying it's an ostrich and not a dog, but even though it looks very similar to the first image. So this is the concept of adversarial images. Then there's something called adversarial artifacts. This piece of research has been done in Carnegie Mellon. So I was there this summer, so I could interact with the research group there. The person on the screen is called Mahmood. He's one of the PhD students working on it. So they have an interesting piece of work here. So they have a face recognition system, and this is the first image that passed. So it says it's Mahmood with 99% confidence. That's fairly simple. Then he removes the spectacles. Even then, it says it's Mahmood with 99% confidence. Nothing too great about that. Now he wears something different. This is a frame which has been 3D printed and put on top of his spectacles. Even then, the system says it's 98%. Now let's do something crazy. What they did here was they took this frame and they 3D printed a textured layer on top of this. Okay, so it's the same 3D printed material, same shape, same form factor as well. Just that the 3D printed a pattern on top of the frame. Now it says it's aerial with 94% confidence. It's not even misclassifying with lower confidence. It's saying with such good confidence that it's aerial. So just by wearing this spectacle, he was able to trick the system into believing that he's aerial and not Mahmood. So just think about it. The implications are just enormous. So here he can trick into any face recognition system. He can get unauthorized access to places where it is not allowed to by tricking systems like these. Any form of biometrics. This has been currently done for images. I think for voice recognition systems also it's fairly the same approach. So even fingerprint scanning, and if you can add a particular layer of film on top of a finger, and you can fool the system into believing it's someone else. So the implications are enormous. Even for self-driving cars, first of all, there's a big question of safety, and the people accepting it is they're not really accepting to self-driving cars. They're just beginning to accept it. So imagine you have a traffic signal and it says it shows red, but if you do something and put a layer on top of this traffic signal and make it appear as if it's green to the system, there could be chaos, there could be accidents, and so you can tamper with self-driving cars like this. And there's so many, you can mess up the signboards and make it believe it's something else. So the any deep learning applications you take, wherever there's gradient descent used, you can fool systems. So I'll tell you a few ways how it's done, how the systems have been fooled. Then I'll tell you why any system which has gradient descent can be fooled in this manner. So we look into a few attacks. So before that, let me just give you a broad classification. There are two kinds of attacks when it comes to the model parameters. So there's something called black box and white box. In black box attacks, you don't really know what the model is. You don't know the architecture of the model. All that you know is this is the input and this is the output. You don't even have access to the parameters or anything from the model. In white box attacks, they are you know what model you're against. Say VGGNet or any model, you know what you're against. You can in few places you can even modify the parameters, albeit as an external party. So, but in real life scenarios, it's mostly a black box attack where you don't really know what architecture is being used. The second kind of classification is targeted and non-targeted. So this one, in non-targeted, what an attacker tries to accomplish is to make sure that the system fails. Okay, so it doesn't really care about what the output is as long as it fails. So I can show you a picture of a dog, and my only objective here would be to not classify it as a dog and classify it as anything else, as long as it misclassifies. In targeted attacks, they're very specific attacks. Say I have a dog and I have a ostrich. I need this dog to be recognized as an ostrich. So I attack in such a way that the dog has to be classified as an ostrich. Okay. So, and another form of classification is one-shot and iterative. It's not that relevant to this talk here. In one-shot, you tamper with the image in just one step. In iterative, you go over small steps. So I won't be covering that aspect here. So let me go through a few popular approaches. The first one, it's a very simple approach. It's called fast gradient sign method. So in a typical deep learning scenario, you have a loss function. You take gradient of the loss function with respect to weights. Then you update the weights so that the loss decreases and reaches a minima, right? But in this case, we are considering it as a black box attack where we don't know the model parameters and we don't have access to model parameters. So you have input, you have model, you have output. So here instead of tweaking with the model parameters, we tweak with the image. So we take the loss with respect to the image. We take the loss with respect to the image, and then instead of going towards a direction which leads to a local minima, we go in the direction opposite to it. So in typical gradient descent, you see there's a negative sign here where you go in the direction opposite to the gradient so that you reach a global minimum, a local minima. But in this case, we go opposite to the direction of the loss. So basically what you're trying to do is you're trying to increase the loss. By doing this, you can make the system misclassify a lot more examples. So I think, any questions on this part? Okay, and this example, it's a form of non-targeted attack. So you don't really care about what the misclassified output is as long as it misclassifies. And this is just an example here. So this is an image of a broccoli. It says it's 99% confidence. This is a particular kind of noise which has been developed using this formula. You have this noise. Now it says it's a green lizard. This was a non. Any
I
question?
just have a question about it. Yeah. Actually, this is like. Can you hear me first?
Oh yes, yes. Carry on.
Okay. My question is, for this method, you need to have the model, so it's a kind of a void, right? Because when you don't have a model, you cannot do the back propagation or like calculating derivatives and this sort of stuff.
Here we're not tweaking with the model parameters, one thing, and there's this concept of transferability. It's called principle of transferability. What it essentially means is, say, I don't really need to know what the model is. I don't even need to have any idea about the model. So as long as I can train my own model with my own architecture on the same domain of images, the adversarial images which I generate from my architecture works well to an extent on the targeted architecture we're looking at. So it's basically because all image classification tasks are solved in a fairly similar fashion. Most of them use CNN layers. Most of them use gradient descent and for backpropagation, and so all these are very constant in most architectures if you look above. So I can take any model which is similar to the typical image classification architectures. Then I can train it on a domain of images which are very similar to the targeted attack. So I can generate adversarial images for my architecture, and it works well even to the targeted architecture we're looking at. Did I answer your question?
Yeah, got it. Thanks.
It's called the principle of transferability. You can look up in case you're interested. So this is a variation of the first one. This is a targeted first gradient sign method, where here we see that you have a true label. You're going away from the true label, so you're basically trying to misclassify. Here we see a negative sign. That means you're going closer towards this target. That means this is your, say in the first image I'd shown, if you want the dog to be misclassified as an ostrich, I would be passing ostrich here. So basically I'm trying to modify the input image in such a way that the output is classified as an ostrich. So basically I'm going towards the point in the loss function where it will say it's an ostrich. So any questions on this? Okay, I'll move forward. This is another example of targeted attack. First, it says it's a koala. I have this noise, and the noise was generated to make the system believe it's a coral reef, and it did, but the confidence is less. But even then, it detected it as a coral reef. So this is a very simple approach. It's just one shot. You just need to calculate one gradient, and then you're able to fool the system. You're not even doing any computations, nothing. Just one step, and you can fool the system. So these are very popular and simple approaches. And this is one approach called one pixel attack. This is very scary because I'm just changing one pixel on the image. So in this, you can see it's supposed to be a ship. I just changed this pixel. Now it says car with 99% confidence. This is a horse. When I change this pixel here, it says it's a frog with 99% confidence. So just by changing one pixel, the whole architecture was fooled. And the way it's a little more sophisticated algorithm than the first one. It follows along the lines of differential evolution. I'm not going to be covering that here. I just want to share it with you in case you guys are interested. You can always look into it. But one thing to note here, personally, I'm not that convinced with this approach. If you ask me why, the images are they have just 1024 pixels. So one pixel out of 1024 is about 0.1%, which is fairly significant. If you take an HD image, in 4K image, it would be around 2000 pixels. So in a way, I'm not that convinced with this approach because even though they say it's one pixel, but one pixel in 1024 is a significant amount, I would say. Those are the popular techniques in attacks, and I won't be covering the defenses in detail. I'm running short on time today. So the first easiest approach is image denoising. So you're basically adding noise. So if you can remove the noise, you can probably save the network from getting attacked. But problem with this is it doesn't really work that well because what it's adding is a particular kind of noise. The noise doesn't even seem to have any impact on the image as far as human perception is considered. So the new image, any questions? Okay, so the new image looks as good as the old image. So there is no significant noise, any perturbations in the image as such. So this method doesn't really work well. And the second kind of approach is called adversarial training. This is more of a brute force approach where when you're training the system, you have an adversarial network too along with it, and adversarial network produces more adversarial images, and you use these adversarial images to pass it to the training system so that the training data set, so that you learn not just with the original data set, but on top you learn on the adversarial images too. I take the misclassified example in the adversarial images. I correct the labels, then I pass it back to the training set, where the adversarial images are sent for training. So basically, you're trying to maximize the possible input images along original set as well as the adversarial set and try learning on it. It works fairly well when you know what attacks are possible. So if I know these are the kinds of attacks I'm trying to resist against, I can generate as many adversarial images from those attacks, train the system, and I can be kind of I can basically make it resistant to such attacks. But the problem here in adversarial training is if I attack the system with some other approach which I have not trained for, it will still tend to fail. So the more attacks you incorporate in the training setting, the better it is, but it's more of a brute force approach. And the final defense, it's called defense distillation. This is a fairly involved algorithm. What they do here is usually in a classification setting, what you actually care about is one class, which is the maximum probability. So you don't really care about what other class probabilities are, as long as the one which is actually true as highest probability. So what they do in defense distillation is they take the final layer out and they try to predict probabilities where I try to match each class probability and not just looking at maximizing one probability of the max class. So to give an example, so if I take MNSet data set, say have 3 and 8, they both can look similar. So you would expect both of them to have similar probabilities. So even though if it's 3, even if I get an 8, it should have a probability closer to 8 than compared to other numbers. So what we try to do in defense distillation is you try to predict probabilities for each class, and you have a loss with respect to each class and not just about one class where probability is maximum. So it's again two-stage network. Your first stage predicts the probabilities. Your next stage takes these probabilities as labels and then gives a final output. So again, I'm not really going into the details of it. I'm not really going into the details of it. So you can ping back anytime on me. So I have a time limit of 30 minutes. So these are common. There's another kind of approach where people use capsule networks, which they say, and denoising autoencoders, they say it works well. So what are the key takeaways from this talk? So I would like to say that we have seen AI coming to its power in the past decade. We've seen so many applications where AI even beats human level accuracy for that. So I don't think it is time yet for AI to take over. So when it has to take over, it has to be robust, not just accuracy wise, even computation wise, even the security aspects of it. I don't want to deploy a face recognition system where I can easily can be attacked and be fooled. So we need to look into ways where you can safeguard our architectures from getting attacked in similar way. And these attacks are not even sophisticated. You can do it very simple. So unless this is my personal opinion, unless AI addresses this issue, its deployment in actual real world scenarios will be difficult. So, and another thing here is, this is again one of my opinions here. Why is it that two images which looks fairly similar to human, it's even imperceptible, but to machines they look very different. So there must be something fundamentally not right about the way in which the machines are learning. So it might be the way it's learning probably now is looking at the lower level pixel wise relationships and then trying to make some assumptions on top of it and predictions on top of it. But we humans, we look at it from a top down approach. We don't really look at pixel wise and then make up our decision that it is so and so thing. So I think there must be something fundamentally different in which you learn, and I don't really know how, but I think for the future, if it has to scale and match up to human level performance in all spheres and not just in one sphere, I think the way these machines learn should change. It should incorporate higher level features as compared to okay. Question. Should I? Okay, I think they're disabled. Is this what you guys want?
Hi, Rahul.
Hi.
Yeah, I was just suggesting that if everyone can unmute their video, or we can take a picture of the session and post it in the Facebook group, or give it to Brenda.
Yeah,
It will be
sure.
good for the.
Yeah, sure. I'll just. I hadn't given access to the video rights. Can you guys start sharing your screen? Is it possible, or should I allow it?
No, we can do it by ourselves only. I think Dharmatej and Ayush has already done it.
Okay. Okay, I'm mostly done with my talk. Any questions? First, I'll just clear it up.
No, the talk has been great. It was really new to me, the adversarial ML.
Okay, that's good. Anyone else? Any questions? I can officially wrap it up. I have probably 5 more minutes until the recording goes shut.
And Rahul, will you be sharing the name of the attendees to Brenda?
I'll make a note of it.
Okay.
If you can give me at least in the put a message on general discussions. Can you reply on the thread? I don't really have your Slack IDs, so it'll be good if you guys can tag me there.
So where should I like, what is your Slack ID? I'll then contact you.
I've put up a message on general discussion about the webinar. You can probably reply to the thread.
Okay.
So I'll stop sharing my screen. And I think if you want a picture.
I think we cannot see the screen of Dharmateja, Ayush and Mitch. Okay, there is a message from Mitch. Someone has left the group. Yeah, I've taken a picture of like we two are only sharing the screens. I've taken a picture. I'll post it. Post this only in the FB group. It will be good for the visibility of your session also.
Yeah, exactly. So anyone else, if you want to share the screen, if you want a picture on the picture.
Just that my net is kind of wonky right now, and if I start the video, the audio goes off.
I'll give it a minute. If no one comes up, I think I'll close the session.
Yeah, sure.
Let me try on such a work system. I think it's, yeah, connection and stable.
Yeah, I've taken a picture. Thanks.
Okay, so I think
I'll tag you all in the Facebook. You are in the group, right?
I'm not.
Yeah.
Okay. So anything else, or shall I just wrap it up? I think
Just one thing,
Dharmateja too. I think did you get into the
Yeah. Yeah, thanks all. I have taken it. Yeah.
Okay.
Thank you.
Thank you guys for attending, and it means a lot to me. I hope you guys learned something new. It is just an introductory section. You can probably look into it in more detail later on if you are interested. And it was great.
Just one thing, Rahul, just one thing. There was a competition on Kaggle, I think a year back, in this adversarial attack.
Okay.
I guess if with the methods that you've outlined, can we, start, just try that competition out with the basics? Or would you suggest some other further reading and all before we try it out?
I think we can right away start. I don't really have any idea about the competition you're talking about, but the methods which I told, they're very simple, and there are a lot more other attacks possible, more sophisticated involved. But this is something very simple and very popular. We can right away use it. You don't even need any competition. You just need one gradient is what all you need. So I think we can try it out. Probably add the link to that competition. We can look into it for sure.
Okay.
Okay, so I'll ending the meeting. Thank you guys. Have a great day.
Thank you.